Hello, everyone. Thanks for joining me today in this spotlight session in which I will be demonstrating how to run some initial spatial analysis on point data using Carto's Snowflake Analytics Toolbox. In particular, today we'll be running some analysis on crime data for home insurance risk assessment. Let me quickly start sharing my screen so we can start by giving you some context. So again, as I said, the plan for today is to use some of the statistics functions available in the analytics toolbox for Snowflake. These are the different functions that we have. For today's session, we're planning to use 3 of them for an initial analysis, as I said before. And the context of this session for today is, well, let's suppose that we are some insurance analysts and we are interested in knowing how crime data or crime in general affects the rate of insurance claims. And we want to understand if that affects and then how can we model that in order to take it into account for home insurance premium calculation. For this analysis, we are going to be using crime data. In particular, we are going to be using this 10 years of crime data in the city of Chicago. For this data, we know their location, their exact location, and also we have the date and time where each of these events happen. For this analysis, also for more context, we specifically filtered and we only are going to consider burglary crime because we identified that that's the most relevant for this type of analysis for home insurance risk assessment. Before we start with the analysis, also just one comment. In this case, we are framing our analysis in insurance, in the context of home insurance. But just bear in mind that since we are using point data and point data for which we have also a temporal dimension, this can be applied to any other analysis in which you have this type of data. So let's start by taking a quick look at what the data looks like on a map. In this case, this is, well, I already have some of these visualizations ready. In today's session, we are planning to do some of this part of the analysis live. This is what the 10 years of crime data in the city of Chicago look like. As you can see, here we can identify some areas where there's no crime, probably because, again, since we are only focusing on burglary, probably no homes are there. But then in the parts of the city where crime happens, it's really hard to identify any pattern here. Okay, so one of the first things that we want to do when we're working with point data is actually aggregating this data into some aerial aggregation. Today we're going to be using H3 spatial indexes, but you can use any other index like Quadbeam, or in case you're interested in other type of geometries, that are also fine. In order to be easier to identify these type of patterns. And why we want to do this pattern thing? Because again, if we go back to the question that we wanted to answer from the very beginning, it's like, okay, so we know that crime normally affects insurance claims, home insurance claims. But in this case, what we want to, so once we know that, the idea is, okay, so can we actually find some pattern in crime in a city, in this case, in the city of Chicago, so that if we can find that pattern, that spatial pattern in the data, then we will be able to model that pattern so that we can actually take it into account for a home insurance premium calculation. So today's session is about this, about looking for this idea of can we actually find a pattern in crime so that afterwards we can model it and take it into account for a home insurance premium calculation. So as I was saying, the first step that we are going to do is aggregate this data using H3 resolution 8. So H3 resolution 8 looks like the following. So I'm just going to plot it here. So let me get rid of the previous information so it's cleaner. In this case, again, what we have done is using H3, as I said before, we are aggregating all the crimes, in this case, burglary crimes that happen in every single spatial index, okay? So that we can have a cleaner view of really what happened in these last 10 years, okay? In order to get this visualization, well, we're using a table that was created using this code here. Okay, so very quickly, basically what we're doing is for every crime, we're assigning its corresponding H3 grid of resolution H3 cell, sorry, with resolution 8. And since we want to make sure that for every cell that covers the city of Chicago, we have a number, we're also polyfilling the city of Chicago so that we're sure that even though in those locations where we don't have crime, we also have a 0 number. So this is what we're doing, and this is what we have as a result. Okay, so again, we are also doing this polyfilling because we also have locations with 0 crimes. So once we do this, this is exactly what we were looking for. So the question is like, can we find any pattern in the data, in crime data in the city of Chicago? The answer is clearly yes, because again, when we look for spatial patterns, this is what we're actually looking for. Okay, so we can see some areas in the map that show very low concentration of crime, while there are some others here in the north and these other in the south that concentrate a lot of them. And when we talk about spatial patterns, it's not just that this thing about north-south, it's also that high values are closer to other high values and low values are closer to other low values, which is exactly what we can see here. Okay, so initially everything looks good because we can actually see a pattern. The next thing or the next step in our analysis would be, okay, so we can see this pattern, but then we need to quantify. So we're probably going to be asked for a number. Okay, so this number is what is called the spatial autocorrelation. So we want to give a number to this relationship. So are things, so this spatial autocorrelation, what actually measure is that are near things more similar than things that are far away. So basically, if I find a location with a high rate of crime, are locations around it also showing a high rate of crime, or the other way around? In this case, we can see that data doesn't look very random. It actually looks like there is some pattern here. So, but let's see, let's calculate this number. So in order to do that, we're gonna be using Morenci, okay, which is the first function, the spatial function that we're using today from the statistics module. In order to run it, this is very easy. As you can see, we just have to input the data, the table where we have our data aggregated in some spatial index, in this case, H3 resolution 8. Then we need to input the resulting table, which in this case, it's the same name with this Morenci suffix, so we know what we are referring to. The name of the column with the spatial index, the variable for which we want to compute the Morenci, which in this case is the count, so the number of crimes that happen in that specific H3 cell. And then we have these two other components, which are the K-ring and the kernel that we're using. That I think it's best if we explain it using the map. With K-ring, what we mean is in order to compute this statistic, so this Morenci, how many rings around every cell we want to consider. So let's say one ring would be all cells surrounding that. Two rings would be like with a distance of 2 cells from the one that we are considering. And then this uniform distribution, or this, uniform kernel, just means that all cells that are considered are given the same weight. We have other kernels, as we will see later, that give different weights depending on the distance to the central cell. But in this case, we decided to give the same weight to all of them, okay? We run this code again. We see that we generate this resulting table. So if we go back to all the tables that we generated here, we just have to go to the Morenci, which is one that stores this information. And we can see that we got a Morenci of 0.51529, which again, Morenci provides a value from -1 to 1. 1 mean perfect autocorrelation. So in this case, 0.5, it's pretty decent. So basically, again, from the very beginning, we saw that there's some spatial pattern here. We can see some exceptions where we have low values very close to high values, but in general, it shows quite a strong spatial autocorrelation. Okay, so once we have quantified this, the next step is, okay, so now we want to actually start modeling this. So we want to see how we can take this into account for calculating home insurance premiums. So the next thing, the next analysis that we are going to run is actually computing hot and cold spots in the city. Okay, so again, because probably we want to apply different rules depending on the concentration of crime that happens in a specific area. So what a hotspot analysis look like, and we will go later to the code, is like this. Okay, so when we run hotspot analysis, what we can expect as a result is exactly what we are seeing here, which is a cleaner view of what we saw before. So sorry, let me go back here. Here again, we can see areas with higher and lower concentrations, but things are a little messy. Let's see to really see anything. When we compute hotspot analysis, we can have a clearer view of what is really happening. Okay, so we can see two clear hotspots in the city of Chicago, and then we can see some cold spots, which probably correspond to parks or areas where there are fewer homes. But then definitely we can see other areas with homes and also a low concentration of crime. One extra analysis that we can do, because well, in order to compute this spatial this hotspot analysis, for this we use the gettysort function, which the gettysort is a statistic or a statistics formula that basically transforms our data into a z-score. So what we need to know is that it allows us to identify hot and cold spots, and the input is very similar to the one we had for more insight. So basically, we need our initial data aggregated in some spatial index. In this case, it's 3 with resolution 8. The output table, and then again, the spatial index column, the variable for which we want to compute this, which is the count of a crime. And then same thing as before, a k-ring and a kernel. In this case, we are using a k-ring of 3. So remember, this is how many cells around. So if we are, if this is my central cell, so how many rings around it I want to take into account in this, for this formula, which is 3 in this case. And then the kernel, in this case, we decided to use Gaussian. If you remember before, we used for more insight, we use the uniform one that gives the same weight to all the cells around it. In this case, Gaussian gives a stronger weight to the central cell and smaller or lower weight as we get further away from the central cell. Okay. Again, one question that you can have is, okay, which one should we use? It really depends on the data, on the use case. If you don't really know, our advice is just to try with different ones, check the results and see which one looks better. So again, in this case, we decided to go for Gaussian. And we want to take a look at the resulting table that we get in this case, is this one. So we have the Kitties one. And as you can see, we have for every H3 cell, we get the GI or GI star, which is the name of this statistic that is generated. And most importantly, since this is a z-score, we get a p-value. Okay, and what this p-value is offering us. So basically, if we add, let me quickly check, this was layer A. So if I can add a new widget for layer A, which we're going to select the range. Let me quickly do it, and then I will explain what this is. But basically, we're going to add a widget on the p-value. And again, if you're familiar with p-values, so basically, if you remember from Statistics 101, a p-value allows us to identify significant values. When we are talking about spatial statistics, a significant value is a value that we assume that doesn't come from a random process. Okay, so that data, that if we look at the data on a map, we identify, or we can identify a value that definitely doesn't come from a random process. It has to, there has to be a spatial pattern happening in that location because that value is extreme, let's say. So in this case, again, from statistics 101, probably we know that normally we use this 0.05. And when we filter by this, these would be the hot and cold spots. Okay, so we have significant hotspots here in these two ones, and then we have several significant cold spots. So again, at this point, we would have more information for this calculation of home insurance premiums, because definitely the rules or policies that we want to apply for the calculation of these home insurance premiums will be different in these areas compared to these other to the cold areas. Okay, so again, very interesting information. Now, as part of the last analysis that we'll run, is that if you take a look at this data, we can see that here we have definitely hotspots. But if you remember from the very beginning, we saw that crime data looked in this hotspot. Actually, we identify some areas with a low number. Actually, we can identify some cells with, for example, here 57 crimes compared to 537. So we have an order of magnitude of difference. So probably there's something more happening here locally. Okay. So, and this is what we want to identify. Another analysis that is very interesting is this, um, what is called local spatial autocorrelation, or also sometimes called spatial outliers. So we want to identify not only that we have some locations with, sorry, let me go back to this map. So we not only want to identify some locations with that are hotspots, we also want to identify if within these locations we identify some outliers, so some exceptions here, because that could also be very interesting for our use case, in this case for home insurance premium calculation. And this is provided by this analysis, which again, I'll later show you the, um, the code. But what we're doing here is uh, we are clustering our data into 4 clusters. Okay, so very similar to the result of Getty's OR, but with a little more of information here, which is we have 2 main clusters, which are the LL and high, which means low cells surrounded by low cells, so low values, which would be, okay, a safe place surrounded by safe places around it. High, which will be areas with high rate of crime surrounded by high rates of crime. And then the important ones are the so-called outliers, which would be low high and high low. Low high would be locations with a low rate of crime surrounded by areas with high rate of crime, and a high low, which is the other way around. So locations with a high rate of crime surrounded by low rate of crime. In this case, this would probably, for us as an insurer, that would be the interesting ones, okay? Because we want to know if an area is going to be considered as a safe place, but inside we have some exceptions. We want to make sure that we identify them. So in this case, in order to compute local Moran psi, the function is called exactly local Moran psi, H3 in this case, because we have H3. The input is the exact same as we used before. So we just have to input the table, the output table, name of the spatial index column, the variable that we are interested in. In this case, we have an extra parameter, which is the number of simulations, because in this case, in order to determine if one location is an outlier or not, we compute some simulations in order to see how far away this is from what would be expected from a random sample, which again, don't worry about this. This just means that we need to run some simulations here. Okay, as a result of this, this is the table that we get. Let me quickly show you. This is it. Okay, so for every index, we have the local Moran psi value, the simulated p-value, which is, again, as before, this is the one that we are going to use to know if we have a significant area or not, and then other statistics that for now, let's just not worry about them. Okay, so let's use the value here again to get more information on our map. So in this case, we can add another widget for layer B. So in this case, we want to add another And let's just also use a range for the simulated p-value. Let's aggregate it using average. And again, since a p-value goes from 0 to 1. And then if we decide to filter as before, so let's consider only those with a p-value smaller than 0.05. In this case, let's just write 0. And this is what we have. Okay, so in this case, again, this information is even richer than the one we had before with Gettysord, because we not only have clear hotspots here and cold spots similar to the ones we had before. Now we have more information, like these light green areas here that are locations with low um, rate of crime, surrounded by areas which initially have a high rate of crime. And then most importantly, we have a specific cold spots where we can have some specific locations with a high rate of crime. Okay, which probably in those areas we want to take a different approach or different rules for home insurance premium calculation. Okay, and well, with this, we finish our initial spatial statistics analysis session. Again, as I said at the beginning, there are other functions, so probably we'll have more spotlight sessions to introduce them. Thank you very much for joining me today, and very happy to get any questions that you may have. Thank you a lot. See you around.